Hello. Good morning, everyone. Okay. From today onwards, we are going to take the revision. Okay. So we'll start from the first chapter. So first chapter is protective relays, right? Total chapters in the syllabus are 7. We covered all the chapters here, and up to the declaration of examination timetable, we are going to take the lectures here. Okay. So protective relays, we have seen what is meant by relay, why these relays are used, and we have seen the different types of relays, right? There are different types of protections. That is, the distance protection is there, equipment protection is there, transmission line protection, right? In equipment protection, there is again the generator protection, transformer protection, alternator protection is there. Different equipments we are protecting by using these relays. So this relay basics we have seen, means what are the types of these relays here, we have seen. So these all are the basic types, and after that, according to the application, we have seen the different chapters here, right? So first is the protective relays. uh, so in this chapter, there are very basic points. So what is mean by this zone of protection? Important points are then primary and backup protection, then different types, that is the attracted armature, balance beam, and moving coil relays. So now these are the basic relays, means the working of these relays, which are used for different applications, right? Then uh, in this microprocessor based relays, that is the static relay and induction relays, and the torque equation is also asked in examination, and they're asking the instrument transformers also. Okay. So what is mean by this protective relay? So we know this protective relay is one device, right? So which is used for detecting the fault. Okay, it is used for detecting the fault, right? It actually not mitigating that fault. It only detecting the fault, and that relay sends the signal to the circuit breaker to open the contacts of that line or of that equipment, which is to be protected, right? So this relay is only detecting the fault, and it gives signal to the circuit breaker. And what this circuit breaker does, this circuit breaker isolates that faulty section uh, from the other, or the normal system here. Okay. So that our line or our system get protected. So this is the switch gear device. Okay. So this relay is a uh, switch gear device. Okay. So why we are using this relay? Because there in our power system there are number of faults occurring in the system, and if that fault occurs, then the whole system gets stopped. Means the supply to the consumer will get stopped, right? That's why we have to. It is necessary to detect that fault. But as the transmission lines are in the kilometers, we should know where actually that fault is occurred, right? That's why we are doing the sections of these transmission lines or the whole power system, and in that we are putting uh, the number of relays Okay, number of relays where we require. So according to that, the particular faulty section will be disconnected, and mm, we can use the system by using the another or the backup protection, right? So we need these relays. We need these relays because they will detect the fault, and we can disconnect that particular part only, and we can protect our equipments. Okay, not only the equipments but also the lines. Okay, then this is the basic circuit diagram of the relay, how actually the relay works. Okay, so definition and working of relay is also asked in examination. So define the relay and working principle of the relay. So how actually this relay works? So here your bus bar is there, then this is the circuit breaker, and these are the CT means current transformer. Here the fault is occurred in this line, and this is the CT primary, and this relay coil is nothing but the CT secondary. These are the contacts, normally open and normally closed, and this is the tripping coil. Okay, then what actually happens here, if any fault will occur under normal working conditions. Okay, first we'll consider the normal working condition here. Under normal working condition, remember the relay contacts are closed या open under normal working condition. Yes, just imagine here there is a no fault. This line is carrying some current. Okay, normal current. So just tell me, what is the relay contacts means, the normally open or normally closed? Yes, the relay contacts are normally closed or open?
Open.
Open, correct. Okay, you should know such basic questions because you are having external examination for this. Okay, so the relay contacts are normally open. Okay, and the circuit breaker contacts are normally closed. Okay, you just see here. Here the contacts are shown open, but when the current will flow through this line, when these contacts are closed. Okay, so the circuit breaker contacts are normally closed and relay contacts are normally open. Okay, means under normal working conditions. Now, when the fault will occur, okay, when the fault will occur, that time this relay coil operates, means the current flowing through this coil increases and these contacts get closed here. Okay, so when the contacts get closed, okay, means when your relay will start working, that time this strip coil, through this strip coil the current will start flowing. Okay, and it will move this contact away from the circuit breaker, means the normally closed contact becomes normally open here. And if the circuit breaker contacts become open, your this faulty section get disconnected from this bus bar. Okay, so in this case your bus bar get protected when the fault is occurred here. Okay, so this is the basic relay construction. Then according to this only, there are different types of the relays. Then these are some desirable qualities of relays. So means there should be fast operation, reliability, selectivity, stability, sensitivity, etc. Okay, so then this point is important, that is the zone of protection. Zone of protection means we have seen that when we are considering a transmission line or a power system, that time from the generating end to the load end, there are this line is uh, this line is means we are doing the partition of that line, means sectionalization of that line, right? Means we are protecting the generator side separately, means there are different zones of the protection. Means here you can see up to for this generator there is a separate protection, for this transformer and generator and circuit breaker one separate protection is there, right? So this one is the generator zone, this is the generator transformer protective zone, right? Then again the circuit breaker zone is different. Now this is for the transmission line only, okay? So this transmission line zone is different. Again for the distributor it will be different. So uh, there are different zones of protection and all these zones are overlapped. Overlap means what? Actually if we miss any of the line to overlap, okay, means we are suppose protecting this generator separately and we are protecting this transformer separately, and in between these two, generator and protector, we are not protecting that line, okay? Then what will happen if the fault will occur there only in between the generator and transformer? Then that line cannot be protected, right? Means it may damage both the transformer and generator. Therefore we are not keeping or uh, a part which is not protected. That's why there will be overlapping. Means if there is no overlap, there will be the dead zone, okay? And that dead zone may cause the fault, okay, and it may damage the equipments also. That's why the overlapping of the zones is there. Means you can see here the generator and transformer protection zone is there, and this is the bus bar, okay? So again this bus bar protection zone which includes the circuit breaker protection. Actually the breaker protection is included in the generator and transformer zone only, but this protection is also included in the bus bar protection zone, right? Means we are using the relay zones. Means what? We are using the relays at the start and at the start point and end point there, right? Means if there are two protective zones here for this circuit breaker, any one of the relay will operate, okay? So and we have seen the operation of the relays also. Whoever relay will operate, there are times given, right? um, Time is given, particular time is given for the operation of the relay, right? Means at a time all relays are not operating, right? There is a time graded system, okay? So these relays are these sections are overlapped here, okay? And these are nothing but the zones of protection. So we have seen why these zones are protected here, overlapped here, okay? And then after that the next one is the primary protection, and second type is the backup protection. So can anyone define this primary protection and backup protection? Primary protection, backup protection, what is mean by this? So primary protection is just like our supply system at the home, right? So when the supply is continuous, okay, that time it is called the primary source of the supply, right? It is the primary source. But when it will fail, but when it will fail, that time our inverter is working, so it is nothing but the backup protection, right? In this way, in transmission lines also there is a primary protection and backup protection. So here you can see the figure. This is the main bus bar, right? Then uh, there is a line, and this is the line bus bar. Means here actually these are the sub lines, okay, used for the distribution purpose, right? So here for this line, uh, actually uh, for these different lines, for the distribution lines here, we are using the relays and circuit breakers, right? We are using the relays and circuit breakers for each line. But suppose what happens, any one of this will fail, or whole this line bus system fails to supply, then that time this backup or secondary protection is used. And here also we are connecting one relay and one circuit breaker. Okay, here also we are connecting the relay and circuit breaker, and this is the overcurrent relay, and 1 second time setting. Okay, 1 second time setting. And here it is the overcurrent relay having 0.6 second time setting. Okay, means actually what here? Okay, means actually what happens here? Here you can see the time setting is there. Time setting means here when your fault will occur, that time at the time of 0.6 seconds, at the time of 0.6 seconds, this relay will operate. Okay, but when this relay will operate for this backup or secondary protection, it is its time is 1 second. Okay, its time is 1 second. Means what? Means what? When your primary protection will fail. Okay, when your primary protection will fail, that is when your relay, which is operating at 0.6 seconds, it's not operating, or it fails to operate. That time the relay, which is for the backup or secondary protection, it will operate, and it will operate for at the time of 1 second. Okay, means its time for the primary protection, time of operating the relay is 0.6 seconds, and for this second, that is the backup protection, the time of operation is 1 second. Means after some time this relay will operate there. Okay, so this is your primary protection and backup protection. But our primary protection is such that we need very rarely this backup protection. Okay, we need very rarely this backup protection because everywhere we are using now the relays and circuit breakers, right? We are using the relays and circuit breakers, and these are protecting these lines, and there are very less chances of failing of the relays to operate, right? So when these will fail to operate, that time only this backup and secondary protection is working there. Okay, now, so this is the backup protection. Okay, then the types of backup protection. So there are different types of this backup protection. Ek minute, just a minute. So relay backup protection. There are three types of this backup protection. First is the relay backup protection. Second is breaker backup protection, and third is the remote backup protection. Okay, means relays backup protection means we are using single breaker for the both primary and backup protection. Means backup relays. Then breaker backup means we are using separate circuit breakers, and remote backup protection means we are using one breaker for primary protection and another backup, another circuit breaker for the another station. Okay, that is the remote backup protection. Okay, then there are different types of this protective release. So this is important. We have seen in this chapter only the electromagnetic attraction release. So there are again three types, that is the solenoid type, attracted armature, and balance beam type. Then induction relays we have seen. So here there are again two types, that is the induction disc and induction cup type relays. And then directional relays are there, that is the reverse current type and reverse power relays. Then relays based on timing are instantaneous, definite, and inverse time lag. So we have seen. Then distance type relays are impedance, reactance, and admittance. We have seen this in the distance protection chapter, right? And then differential relays, that is the current differential and voltage differential relays. So these relays are used for the equipment protection, right? We are using here current differential relays, right? Differential relays we are using for the transformer protection, then for the alternator protection, right? We are using. And then other types means under voltage current power relay, right? Then over voltage, over current, and power relays. Then thermal relays, rectifier relay, permanent magnet moving coil relays, then static relays, and gas operated relays, right? So these all are the different types of relays. Then there are different definitions. So normally open contact, close contact, operating force or torque, restraining force and torque, then pickup level, dropout or reset level. So these all are required for the operation of relay. So here we are requiring first is the operating torque, right? Then restraining torque, right? Operating means something which is helping you to operate or do some work, right? So there is a one operating coil and another one is the restraining coil. Operating coil is what actually it doing, it is attracting that arm so that the relay contacts will get closed, okay, to operate the circuit breaker. But this restraining coil is forcing, means that arm, okay, to open the contacts, okay, means there is one spring, okay, means it opposing that operating force or torque, okay. म्हणजे ते रिले कॉन्टॅक्ट क्लोज होऊ नये त्यासाठी जो फोर्स अप्लाय केला जातो दॅट इज नथिंग बट युअर रिस्ट्रेनिंग टॉर्क or restraint force. Then pickup level and dropout level. We have seen this pickup level means actually at what level of that may be the current, that may be voltage, or that may be power. So according to the your actuating quantity, so when that value will be reached, then only your relay will start operating. Then dropout or reset level, okay, means that level of current or voltage when your relay contacts will come to the normal operating condition. Okay, that is the dropout or reset level. Then operating time, reset time. So very simple definitions are there. So these definitions also can be asked in examination. Means they are asking you the definitions or the MCQ question. Okay. Then next one is the what is mean by this electromagnetic relay. So whatever we have seen here in the definitions, okay, that is the operating coil and restraining coil. So here it is shown. in electromagnetic relays means it is the general construction of your relay. So here you can see one electromagnetic magnetic is there, then one spring is there, and this is the armature, or we can see the arm. uh, then there is actually air gap between this arm and this contacts, that is the shading coil. Now what happens, and these are the normally closed and normally open contacts of your relay coil, then of your relay, your relay is normally open, the relay contacts are normally open. So under normal working conditions these contacts are normally open, but when the fault will occur these contacts get closed. So what, how actually these contacts get closed? Because here is one electromagnet, means there is uh, one operating coil. So here also it is shown, this is the moving armature, the same is here. This is the operating coil, right? Then control spring is there, then the contacts here. Okay, moving contacts, fixed contacts. Okay, so the same is shown here. So what actually happens when you are under normal working conditions, these contacts are open, but when the fault will happen, the current flowing through this coil increases. Okay, actually the coil is found on this electromagnet. This is the core and this is the coil which is found on this electromagnet. And when the current flowing through it will increase, then its magnetic field also increases and it will attract this arm towards these points, okay, or towards its contact. So when it will attract that arm, that time these contacts, the normally open contacts get normally closed here. Okay, normally open contacts get normally closed, and here you can see uh, that signal will be given to trip the circuit, means it is given to the circuit breaker to open the contact. So this is the basic working of your electromagnetic relay. Okay. Then there are different types of these electromagnetic relays. So actually here electromagnetic relays basic working or that basic relay construction is given there, but according to the construction, there are different modes of this working also. So different types of these electromagnetic relays are: first is the attracted armature type, then induction disc type, induction cup type, balance beam type, then moving coil type, and polarized moving iron type relays, right? So uh, uh, these all are the electromagnetic relays, right? So we have seen after that the modification is done and static relays came, right? So after static relays the microprocessor based relays came, and after that again the numerical based relays came. Okay, so these numerical based these are also the microprocessor based relays, but these are having so many advantages, right? So we have seen that also. Then uh, first type is the attraction armature type of relay. So here the construction is same. Okay, construction is same. So uh, here you can see that spring which is holding that arm in the normally open position, and when the fault will occur, that time the contacts get closed here. Okay, means the current will flow current will flow through the operating coil will be more that time, and that arm get uh, uh, closed with that operating coil contacts, okay, or the shading coil. Then this torque equation also we have seen, right? So this is important one, because in many times this question is asked, the torque equation. Okay, so for the attracted armature, here we have to consider here the general equation for the force, uh, then phi, then r. Phi, from the magnetic circuits, this F is equal to I into N. Then uh, phi is equal to mmf divided by r. This is nothing but actually the reluctance, which can also be denoted by s. Okay, yes. So this phi is equal to mmf. Mmf is nothing but the I into n, or here you can write this as n into I. So this is ni divided by r. Okay, this r is nothing but the reluctance, remember. And then you can write the another equation for the reluctance, that is L divided by mu 0 into A, right? Now this is for the air gap we are considering, and it is proportional to Lg. Okay, so you can equate these equations, and you will get the equation for the force. Okay, and then we are getting the constants k1 and k2 here. Or we can write the equation for current I as square root of k2 divided by k1, which is equal to constant. Okay. So that equation is important uh, uh, in at the first chapter only. uh, we have seen that expression in detail. So everyone try to check that equation from the notebook, uh, if you have noted that. Then the next one is the balanced beam type of relay. So in balanced beam relay, here a separate restraining coil is there and operating coil is there. Then one hinge is provided there, and this one is the beam, right? Then these are for the normally open and normally closed contacts, right? So under the normal operating condition, means when there is no any fault, then that time this beam is balanced. Okay, beam is balanced, and when the fault will occur, that time the current flowing through this operating coil will increase, and these contacts get closed here. Okay, these contacts get closed. This is called the balanced beam relay. Okay, then you've seen the moving coil type relays. Moving coil. So uh, uh, there are two types of these moving coil relays. First is the rotary moving coil relay, and second is the, what is that type? Second type. First is rotary and second is axial type relay. Okay, so first is the rotary moving coil relay. So in this rotary moving coil relay, here one permanent magnet is used, and another is the moving magnet. Another is the moving magnet, right? So and this is for giving signal to the circuit breaker. And here, at this moving the magnet or coil, there is one moving contact, and this one is your fixed contact. Okay, this is your fixed contact. So actually what happens here, so when there is a normal working condition, that time these contacts are open. But when the fault will occur, that time the current flowing through this coil will start increasing, because there will be more magnetic flux produced, and these contacts will get attracted here, means the contacts get closed. And if these contacts get closed here, then your circuit breaker will start operating here. Okay, so here there is one graph of current, time versus current, means if the current starts increasing, the time required for the operation of relay will decrease. Okay, and this is applicable for most of the relays. When the current flowing through the coil will increase, then the time required for the operation will decrease, right? So we have seen the practical on electromagnetic relays, and in that we have seen, uh, or we have seen when the current is increasing, how actually the time required get decreases, right? So we have seen that IDMT characteristic. Okay, then so second type here is the axial moving coil relay. Axial moving coil relay. So first was the rotary moving coil, and second is the axial moving coil. Here only what is changed, there is axially suspended coil. Okay, axially suspended coil is there. So means like this axial movement is there, and there was rotary movement. Okay, so in between these two magnets, there was a rotary movement, and here it is the axial movement. Okay, uh, then we have seen the induction type relays. So there are again different types of this induction type, that is the induction cup type relay, induction disc type relays. But these induction relays, induction, you know, the electromagnetic induction. So these induction relays works only on AC supply, right? AC supply. So there are here the advantages are given, that is it is having the high, low, and adjustable speeds, and it is more accurate. So induction curve type relays are there, and induction disc type relays are here. So, in this induction disc relay, again there are two types. First is the shaded pole structure, and second is the watt-hour meter or double winding structure. Okay. So, what is meant by this shaded pole structure? Shaded means means the coils or the poles of uh, are shaded there. Okay, are shaded. So, and watt hour meter or double winding structure means it is just our energy meter construction. Okay, and then induction cup structure is there. So we'll see one by one here. The shaded pole structure. So shaded means here you can see one is the permanent magnet, and here this is the these are the mm, uh, maintenance or the operating coils. Okay, so spring is there. Then this is the disc, right? Because uh, this is the induction disc type of relay, right? Means the disc is provided here, and this shading is used here. Shading means what? One copper coil actually for this pole. Okay, there are two poles right here, one is this and this is one, and one pole means half part of this pole is shaded by this copper coil. Okay, this is shaded. Okay, that is nothing but the shading. So here it is shown, and here this is your disc, right? So in our electro mechanical relays we have seen this disc also, right? So how was our disc rotating? There was time, right? uh, we can set the time there, and under normal operating conditions what happens, your disk rotates, uh, but when the fault will occur, that will um automatically return to its position. Means when these contacts get closed, okay, that time that will again the disk will come to its position. Okay, means it will stop the rotating. Okay, so this disc is of aluminum here. Okay, so remember. So I hope that everybody this shaded pole structure understood, right? So what happens actually? The torque is produced here. Torque is nothing but torque is proportional to phi 1 phi 2 sine alpha, right? So the combination of these two fluxes will produce the torque there, and your disc will start rotating here. Okay, so the basic working principle is used, which all of you knows. And then the second type is the watt hour meter, or it is also called the double winding structure. So in this watt hour meter or double winding structure, so it's all of you present. Yes. Okay. All of you present. Who is present in the lecture? Okay, Ashwini. So, watt hour meter or a double winding structure, right? So, here again, uh, this is just like our energy meter, right? So, here two windings are used. That's why it is called the double winding structure. Double winding means what? Actually, this is your primary coil, and this is the secondary coil, and there are two magnets. One is the E-shaped magnet, and second is the U-shaped magnet. So here, uh, this E shape is called the upper magnet, and this is the lower magnet, and this is your primary coil, or it is also called the relay coil. And when the current will flow through this coil, it will set the flux. Okay, it will set the flux in this magnet or in this core. Then what happens? There is one more coil which is wound on the same magnet, right? So the flux produced by this first coil will link with the second coil. Okay, it will link with the second coil, and due to that, the current will start flowing through the secondary winding also. Okay, the current will start flowing through the secondary winding also. And when current will flow through the secondary winding, that time this disc will start rotating. And the uh, if fault will occur, that time this relay contacts will get closed here, and the signal will be given to the circuit breaker for tripping the circuit. Okay. Then so the torque equation everywhere is same for your induction type of relays. So this is nothing but the equation of the induction motor. You have already studied this, right? It is nothing different. Okay. What was that equation? The same equation was there. There only you considered the currents, that is torque is proportional to I1 I2, right? Sine phi. Okay, and here we are considering the flux. Okay, then the next point is the induction cup type of relay. Cup type means only there is a cup structure. So here means in one uh, only there we are using here four poles. Okay, we are using here four poles. So there are two coils only, and these two coils, okay, you can see here, these are wound in series on two poles. Okay, one coil is wound on the two poles and it is in series. Okay, so there are different advantages of this cup type structure, because when we are using this watt hour meter or induction disc type structure, that time uh, uh, means what we just like inertia means some vibrations are there. Okay, but at this inner side only we are using the four poles here, that's why these vibrations are decreased here. Okay, so here somewhere that point may be. So it is suited as directional or phase comparison units and have steady non-vibrating torque, right? So here the torque produced by these poles is non-vibrating or it is steady. Okay, that's why this induction cup type of structure is used. Then electromagnetic induction principle. So this is the basic how actually it get produced, the torque get produced. Then next point is the static relays. So what is mean by static? So when we are considering the electromagnetic relays, these electromagnetic relays are having moving parts, right? But in static relays, there is no moving part. Okay, no moving part is there. So here we are using rectifier. There is a relay measuring circuit, amplifier, output device, and this is your DC supply. Okay. So here the secondaries of CT or PT or a transducer and relaying quantity means whatever be the current or voltage which is obtained from the CTs or PTs, or if there is any another device we are using, then we can use the transducer for the conversion to the electrical quantity, and then the rectifier is used. Then rectifier is used for AC to DC, and then relay measuring circuit is there. Okay, relay measuring circuit. So in this relay measuring circuit, what actually done? So this is our actual power supply, and if the fault will occur there, so whatever be the current flowing through this will be compared here. Okay, means if it is false, means the actual current or if this current is greater than the actual current, then uh, it is given to the amplifier circuit, output device, and then to the trip circuit, means to the circuit breaker for the operation. Okay. Then there are some advantages of these static relays, but these static relays are not mostly used here. In the states, we are using the microprocessor based numerical relays, okay, which are frequently used, and also the electromagnetic relays. So these static relays are having so many limitations. That's why we are using the numerical or microprocessor based numerical relays. Okay. Then we have seen the instrument transformers. So all of you know about these instrument transformers. These are used to decrease the level of the voltage or currents, right? So there are two types of these instrument transformers, that is the current transformer and potential transformer, right? So the current transformer decreases the level of current from which ampere to which ampere? From 100 ampere to 5 ampere, and for the potential, that voltage can also be reduced to 110 kV, right? Maximum voltage, which is measurable. Okay, which is measurable. So here, the construction of these transformers is shown. That is uh, here. This is your potential transformer, right? So we are connecting one coil parallel here, right? So this is your potential transformer, primary winding, secondary winding, and here we are using 1 voltmeter, which is measuring that voltage. Means this higher voltage, which is not measurable. So by connecting this potential transformer, we can measure that voltage also, right? Then this is your current transformer, the primary, secondary, right? So uh, at the secondary side, we can measure the current here, and that current is of 0 to 5 ampere. Okay, then CT burden. Burden means actually what? Current transformer burden. Burden means actually what? So it is nothing but the bearing capacity, right? So we from our only you can consider what load you can bear. Okay, that is your normal condition. But sometimes what happens, you have to take some more load. Okay, and what is that extra load you can bear? Okay, what is that extra load you can bear? That is nothing but the CT burden. Okay, means actually burden is some additional load which you need to bear. Okay, that is the extra load. So what happens for the current transformers? For the current transformers, sometimes the extra load they have to bear, and that is nothing but the CT burden, and this burden is measured in volt ampere. Okay, it is measured in volt ampere. So it is mainly in point only. Okay, point only. So here one example is given, 10 volt ampere at 5 ampere. So burden for 5 ampere is 10 volt ampere. So here 5 ampere is the rated CT secondary, right? So for our HGP lab, we used all CTs of 5 ampere only, and the voltage across the secondary is 2 volts here. Okay, so of course the current, if the current is 5 ampere, the voltage is 2 volts. That's why this burden is 10 volt ampere here. Okay, now the knee point voltage. Okay, so what is mean by this knee point voltage? Okay, so actually we have seen the current transformer, right? So for this current transformer, there is particular, the primary current is there, the secondary current is there. So what happens when we are increasing that current? Okay, when we are increasing that current, at that time how actually your secondary is operating, right? How actually your secondary is operating means, here after or beyond this voltage, the linearity between primary and secondary of the circuit, current transformer does not work anymore. Okay, means what happens there? There is a actually linear characteristic most of the time, but uh, we know that means this is for the normal working conditions at least. Okay, there is a normal work operating characteristic, but this is very rare condition that the knee point will occur there. So means what happens, it is just like the saturation, means of your magnetic core. Means when you you are applying some current and the flux set in the core. Okay, and what happens, you start increasing the value of current, and in that ratio only the flux set in the core will also increase, right? But when your core will get saturated, after that if you increase the value of current, then the flux will not increase, the flux remains constant. That is nothing but the saturation of that core. The same is here also. Means there is a linear characteristic between this voltage and current, but after saturation, okay, after saturation, if you increase that current, the voltage remains constant, and at which point it will start remaining constant, okay, or it drop to, or it stop to increase. That is nothing but your knee point, okay. Then this is the microprocessor based relay. So these microprocessor based relays are important, and this is the very primary construction of this microprocessor based relay. So here we are using the current transformers, right? Then current to voltage converters, rectifiers, then multiplexer, A by D converter, and this is your microprocessor. So these all operations are done in this microprocessor only, and this signal is given to the circuit breaker. Okay, the signal is given to the circuit breaker for the operation. Okay, so microprocessor based relay. So this is your last point, and this is the flow chart, right? Okay, then there are different types of these potential transformers, that is conventional wound type and capacitor potential transformers. Okay, there is a string of the capacitors, right, in capacitor potential transformers. Okay, and conventional wound type or electromagnetic type transformers. Okay. So these microprocessor based relays are important. We have seen these relays in second and third chapters, right? So here we have completed the revision of first chapter. We'll see uh, in upcoming lectures if it is necessary. Okay, so for today we'll stop here. Thank you all and have a nice day. Thank you.